So, my dear student friends, back to the class. After last class, in the last class what we did is, we tried to know how to estimate the diffusion coefficients when diffusion coefficients values are not known. That means maybe we can use some theoretical expressions or semi-empirical expressions based on the kinetic theory of gases. That is what the proposal by Wilkie and Lee for the gaseous systems and Wilkie-Chang equation for the case of liquid systems. Then we also discussed something about estimation of diffusion coefficients experimentally. And what we did is, for the gaseous systems, we have like a twin bulb method, and we have a Stefan's method, and a Stefan's method is a more common method, and we discussed at length how to perform a Stefan's experiments and estimate the diffusion coefficients. Then for the liquid systems, we have two horizontal cylinders, and these two horizontal cylinders are separated by a porous plate. Then proper stirring is provided. Then A is flowing from higher concentration to the lower concentration, B is flowing to the higher concentration to the lower concentration. At time t is equal to 0, we stop the process, and at time t is equal to 0, we know what are the concentration. From those concentration one can estimate the diffusion coefficients. And today what we are going to discuss, about how to estimate the diffusion coefficients. And one problem just I will read for you. I don't want to write here because I am leaving the material with you. Estimate the diffusivity of N-butanol vapor through air at 1 atmosphere pressure and 59 degrees centigrade. The data what it is given, the molecular weight of N-butanol is 74, the molecular weight of air is 29. For air, epsilon B by K is equal to 97. The molar radius is 0.3617 nanometers, and group contribution atomic volumes for carbon it is 0.0148, for oxygen 0.0074, for hydrogen 0.0037, and RA is given by 1.18 into V to the power of 1 by 3. The normal boiling point temperature of N-butanol is 117 degrees centigrade. The collision function data is given as Kt by epsilon versus f of Kt by epsilon, that is Kt by epsilon, f of Kt by epsilon, and 1.72, we have 1.5, 0.6 and 2.54. So Kt by epsilon value versus f of Kt by epsilon values are given. Your objective is to estimate the diffusion coefficient of butanol vapor in the atmospheric air, in the air. For air, the epsilon B by K is equal to 97, Rb is equal to 0.3617. For butanol, the epsilon A by K value is not given, whereas the Tb, normal boiling point temperature, is given as 117 degrees centigrade. And similarly, Ra, that is the molar volume of the butanol, is not given, but whereas the atomic values for carbon is given as 0.0148, for oxygen 0.0074, for hydrogen it is given as 0.037. Now what we have to do, we have to estimate the molar volume of butanol. The molecular formula of butanol is C2H5 CH2 CH2 OH. That means we have 10 atoms of hydrogen, we have 1 atom of oxygen, we have 4 atoms of carbon. Then atomic volume of hydrogen is going to become 10 0 0 0.37, and this is going to becomes 1 into 0.0074. This is equal to 4 into 0.148. So the total V, that is A atomic molar volume of butanol, is equal to 0.1036, and your RA is given as 1.18 into VA to the power of 1 by 3, that is going to become 0.5542 nanometers, and your RAB is equal to RA plus RB by 2, that is equal to 0.458 nanometers. Then we have epsilon A by K is not known, but this value is known. Epsilon by K is equal to 1.21 into TB, where TB is nothing but 117 plus 273, that is equal to 471.9. So epsilon A by B by K is equal to a geometric mean of epsilon A by K, epsilon B by K, that is equal to 213.94. Epsilon A by B into K by T is equal to 213.94 divided by 332, that is equal to 0.644. So KT by epsilon AB is equal to 1.552. Now one can plot a graph between KT by epsilon AB, f of KT by epsilon AB, because for every value of KT by epsilon AB, f of KT by epsilon AB is known. So you can plot a graph, and for this situation your KT by epsilon AB is equal to 1.552. So we are going to get f of KT by epsilon AB, and you can note down that f of KT by epsilon AB. Once after obtaining all these values, one can calculate the diffusion coefficients by Wilkie-Chang equation, where DAB is equal to 10 power minus 4 into 1.084.249 1 by MA plus 1 by MB t to the power of 3 by 2 square root of 1 by MA plus 1 by MB divided by PT into RAB whole square f of KT by epsilon AB. This is 0.6. So every value is known to us now. We can substitute all these values in this expression. When you substitute these values, 10 power minus 4, 1.084, 0.249, 1 by 74, 1 by 29, t to the power of 3 by 2, 332 by 3 by 2, square root of 1 by 74, 1 by 29, PT 1.013 into 10 power 5, 0.458 square into 0.6, that is equal to 1.01 into 10 power 5 meter square per second, or 0.1071 centimeter square per second, that is diffusion coefficient of A in B. So that is, we are using a Wilkie-Jang equation for the estimation of diffusion coefficient of A, that is nothing but butanol in air. So that value is coming around 0.1071 centimeter square per second. So this problem is going to clearly explains when the diffusion coefficient values are not known, and one can use these expressions and we can calculate. So now the next problem we can work it on for the liquid systems, how to estimate the diffusion coefficients of liquids. The problem is estimate the diffusivity of mannitol. I think all of you know why we are going to use a mannitol. This mannitol is used for the people paralysis problem. This mannitol it is given to dissolve the clattings in the human body. So here the question is estimate the diffusivity of mannitol in a dilute solution in water at 20 degrees centigrade. Compare with the observed value of 0.56 into 10 power minus 9 meter square per second. Mannitol molar volume at normal boiling point temperature is 0.185. Association factor for water is 2.26 and the solution viscosity is 1.005 into 10 power minus 3 kgs per meter square per second. Viscosity of water 1.005 into 10 power minus 3 kgs per meter per second. So here all the values are given and we have to plug these values in the Wilkie equation, where the Wilkie equation is used for the estimation of diffusion coefficients in the liquids, right? And you know Wilkie-Jang equation, DAB 117.3 into 10 power minus 18 pi MB to the power of 0.5 into T divided by mu into VA to the power of 0.6. So here 117.3 into 10 power minus 18, pi is given as 2.26 into molecular weight of water is 18.02 to the power of 0.5 and temperature is 293 divided by mu, that is 1.05 into 10 power minus 3, and VA, that is the molar volume of mannitol, is a 0.185 to the power of 0.6. That is going to becomes 0.602 into 10 power minus 9 meter square per second. This is what 0.0602 into 10 power 5 centimeter square per second. And the actual value, experimentally estimated value, 0.56 into 10 power minus 9 meter square per second. And if you can compare these two values, the difference is only of 0.04 into 10 power minus 9. And that is what the Wilkie-Jang equation can be used for the estimations of diffusion coefficients of liquids when these values are not known. Then the next problem is on Stephen's experiment. In this case, an Arnold cell is used to measure the diffusivity of a stone in air at 20 degrees centigrade and 100 kilopascals pressures. At time t is equal to 0, the liquid stone surface is 11 mm from the top of the tube, and after 8 hours of operation, the liquid surface drops to 20.5 mm. If the concentration of a stone in air that flows over the tube is 0, what is the diffusivity of a stone in air? At 20 degrees centigrade, the vapor pressure of a stone is 24 kilopascals and the density of a stone is 790 kgs per meter cube. So this is what we have discussed about the Stephen's experiment. And the Stephen's experiments, as we discussed, we have a narrow tube, and this narrow vertical tube is connected with the horizontal tube, and this horizontal tube is the Stephen's experiment. And here the gas is flowing and here we have a liquid level, and at time t is equal to 0, Z is equal to Z naught, which is equal to 11 mm. And when you stop the experiment, the liquid level falls to a value t is equal to 8 hours. The liquid level drops to a 20.5 mm. And we have already derived the expression for the estimation of diffusion coefficients of acetone in water, acetone in air, using a Arnold cell, RT, PBM, rho A, Z1 square, Z0 square divided by 2 into PT, MA, PA1, PA2 into T. And it is given that the gas is pure gas, it does not contains any acetone, that is PA2 is equal to 0. PA1, that is partial pressure of acetone at gas liquid interface, and if the surface is saturated, that is the partial pressure of acetone at a location 1 is equal to vapor pressure of acetone at location 1. And at temperature T, it is given that the vapor pressure of acetone is equal to 24 kPa at 20 degrees centigrade, that is 24 into 10 power 3 pascals. PB1 is equal to PT minus PA1, that is equal to 76,000. And we have to calculate PBM, that is PB2, PB1, ln of PB2, PB1, that is equal to 10 power 5, 76,000 divided by ln of 10 power 5, 76,000. That is going to become 87451 into 8 pascals. And the density of acetone is given as 790 kg per meter cube. Now, if you plug all the values into this expression, it is going to become 8.314 into 293 into 87451.8 into 790 into 20.5 whole square 11 square into 10 power minus 6. This 10 power minus 6 is coming because here it is in terms of millimeters, that we have to convert into meters. 10 power minus 3 multiplied by 10 power minus 3, it is going to become 10 power minus 6 whole divided by 2 into 10 power 5 MA molecular weight of acetone, that is 58, and PA1 24,000, PA2 is 0, and we have 8 hours of operation. To convert that time into seconds, we are going to write 3600, that is going to become 6.3 into 10 power minus 6, and maybe in the practical classes we are going to learn how to operate your Stefan's experiment, and there we are going to use the same expressions and we are going to find out the diffusion coefficients. So this is the problem of estimation of diffusion coefficient when an experiment is performed. Then the next problem is, here in this case, multi-component mixtures. Already we have discussed, if the binary diffusion coefficients are given, Then how to estimate the diffusion coefficients of a component in a multi-component mixer, and at the same time the diffusion coefficients values are given at one conditions, but experimental values are at some other conditions. Now the problem is ammonia is diffusing through a stagnant mixer containing 1/3 of nitrogen, 2/3 of hydrogen by volume. The total pressure is 206 kilonewton per meter square and temperature is 55 degrees centigrade. Calculate the rate of diffusion of ammonia through a film of 0.5 mm thick when the concentrations of ammonia on either side of the film are 10% and 5% by volume. The diffusivity of ammonia in nitrogen at 25 degrees centigrade and 1 atmospheric pressure is 1.3 into 10 power minus 5 meter square per second, and diffusivity of ammonia in nitrogen at 25 degrees centigrade and 1 atmospheric pressure is 4.1 into 10 power minus 5 meter square per second. And if you see this problem, we have ammonia and it is flowing through a mixture of gases, that is 1/3 of nitrogen and 2/3 of hydrogen. That is a multi-component mixer. The total pressure is at 206 kilonewton per meter square and temperature is 55 degrees centigrade. Whereas the diffusion coefficients values are given for ammonia in nitrogen at 25 degrees centigrade and 1 atmospheric pressure. Similarly, the diffusion coefficients of ammonia in nitrogen at 25 degrees centigrade at 1 atmospheric pressure is given. Now these diffusion coefficient values are to be converted to your experimental given values of 206 kilonewton per meter square and temperature of 55 degrees centigrade. The thickness of the film is 0.5 mm thickness and the concentration of ammonia on the either side of the film is 10% and 5% by volume. So here the problem can be represented as, here we have a 1/3 of nitrogen plus 2/3 of hydrogen, and we have ammonia and the concentration of ammonia is 10% here and it is the 5% here, and these concentrations are given in terms of volume. As all of you know, for a gaseous systems the volume percentage is equal to mole percentage. Volume percentage is equal to mole percentage. So that means here the nitrogen and hydrogen is given as in terms of volume percentage, and straight away one can take it as mole percentage. And the ammonia concentration is also given in terms of volume percentage. It can be taken in terms of mole percentage. And the total pressure PT is given as 2.06 into 10 power 5 Newton per meter square, and the temperature T is given as 55 degrees centigrade, that is equal to 328 degree Kelvin. Now diffusion coefficient at condition 1 is given, at condition 2 we have to estimate, and we can use that Wilkie-Chang equation relationship, T1 by T2 to the power of 3 by 2 P2 by P1. Now DAB1 DAB2 is equal to DAB1 T2 by T1 whole to the power of 3 by 2 P1 by P2. Now D of NH3 nitrogen is equal to 1.32 into 10 power minus 5 328 divided by 298 1.5 1.013 10 power 5 divided by 2.06 into 10 power 5, that is going to becomes 0.75 into 10 power minus 5 meters per second. Now D of ammonia in nitrogen it is equal to 4.1 into 10 power minus 5, 328 by 298, 1.5, 1.013, 10 power 5, 2.06 into 10 power minus to the power of 5, that is equal to 2.33, 10 power minus 5 meter square per second. So what we did, the diffusion coefficient values are given at location 1, the diffusion coefficient values at location 2 we have to calculate, and that is what we have done here. Then that now ammonia is now moving in the multi-component mixture of nitrogen and hydrogen, and where nitrogen and hydrogen are not moving, and already we have derived expression diffusion coefficient of ammonia in a multi-component mixture M is equal to sigma of yi by dai, that is equal to where I is equal to B to N. We are not going to take A into the consideration. So that is nothing but YB by DAB, YC by DAC. If you take B as nitrogen, C as hydrogen, 1 by 1/3 of DAB, 0.75 into 10 power minus 5 plus 2 by 3, 2.33 into 10 power minus 5. This is going to becomes 1.37 into 10 power minus 5 meter square per second. So the diffusion coefficient of ammonia in the multi-component mixture is given by 1.37 into 10 power minus 5. Now, as we have done in the previous problem, now you know the diffusion coefficients, and now the two situations we are talking about. We are talking about a situation where non-diffusing B, we have to estimate the flux, and for the estimation of flux, the flux equation NA is equal to DAB into PT RTZ PB ln PA1 minus PA2. Here a mole fraction of ammonia at location 1 is the 10%. So your PA1 according to the combination of ideal gas law and law of Dalton, PA1 is equal to PT into YA1, that is equal to 0.1 into 2.06 into 10 power 5, that is equal to 0.206 into 10 power 5 Newton per meter square. Similarly, PA2 is equal to 0.05 into 2.06 into 10 power 5, that is equal to 0.103 into 10 power 5 Newton per meter square. Then we have PT is equal to PA1 plus PB1, that is equal to PA2 plus PB2. So PB1 is equal to 1.854 into 10 power 5, PB2 is equal to 1.957 into 10 power 5. Right? Now we have to estimate the PB ln. That PB ln is equal to 1.905 into 10 power 5 Newton per meter square, and our film thickness Z is equal to 0.5 mm, that is equal to 10 power minus 3 meters. So now if I have all these values, I can substitute into this expression, and I can get it as 1.37 into 10 power minus 5 into 2.06 into 10 power 5 divided by 8.314 3828.5 into 10 power 3 minus 10 power 3 0.206 into 10 power minus 5 103 10 power 5 1.905 10 power 5, that is equal to 1.2 10 power minus 4 kilomoles per meter square per second. So this is the problem, consists of three things. One is the diffusion coefficients values are given at one condition. The diffusion coefficient values we have to calculate at a condition 2. Then it is not a simple binary mixer, it is a multi-component mixer, and already we have discussed about how to estimate the diffusion coefficient of a component A in a multi-component mixer, and we have discussed about a special case where other components are not moving except the component A. Then we simplified the expression and we can estimate the diffusion coefficient of component A in a mixture of gaseous, and by using that formula we were able to estimate diffusion coefficients of A in a mixture of gases. Once if you get that, the remaining problem is so simple, because it's a non-diffusing B case. We know partial pressures at location 1, we can calculate the partial pressures at location 2, and after knowing all those things, plugging into the expression of your Na is equal to this expression, we are going to get 1.12 into 10 power minus 4 meter square per second. So this is some problems related to your the molecular diffusion through the fluids, and in the next class what we do, we are going to discuss something like what are the analogies existing between the three transports. What are those three transports? We have a momentum transfer, we have a heat transfer, we have a mass transfer. So we have three transports are there. What are the analysis between these three transports? As already you know, we talk about Newton's equation, we talk about Fourier's law of inconduction, and we talk about Fick's law equation on the other side. So we will discuss about what are the analogies or what are the differences that are existing between each transport operations, and then we will discuss about diffusion through the solids. In the case of diffusion through the solids, we are going to get several of the examples where the diffusion through the solids are going to take place. And one example I can give you, when you take a wood, and when you cut the wood from the tree, that wood contains lot of moisture, and this wood cannot be used for making of your doors and windows. At that time what we do is we expose to the dry gas. Now the moisture will be evaporating. That is a diffusion through the solid is going to take place. And at the same time we have a very interesting example. When you make your mango pickle, and the first day when you see the taste of the pickle, you don't find anything. But as the time is progressing, the juice that goes into the pickle, that is again diffusion through the solid is taking place, mass transfer is taking place, and you are going to get some taste for the pickle. But if you leave it for a long time, more and more amount of juice goes into the pickle, and now the pickle structure is going to be collapsed. So that is the reason maximum we can store the pickle maybe 6 months or 7 months, but as the time is progressing, maybe let's say 1 year time, you find only the shell, we don't find anything about the pieces, because so much of mass transfer has occurred into the mango pickle, and the whole pickle has dissolved, and it make it as some sort of a semi-solid type of things that are going to be taking place. So this is another example where we talk about diffusion through the solids. Then the next example that we discuss is nothing but controlled drug release system. That is, when we have some problem like a fever and other things, and when you go to the doctor and the doctor says for every 8 hours you have to take a new tablet. The reason behind this is, when you take the capsule contains a drug. Now the concentration of the drug in the body outside the capsule is 0. So now what will happen? The concentration of water inside the capsule is 0. So the water will be diffusing into the capsule. It dissolves the drug. It will carry back into the bulk of the solution. So where the diffusion through the solids are taking place. Other than this, as we have discussed, we are going to come across several of the applications of mass transfer separation process. That is the new separation processes, that is nothing but a membrane separation process, where we have a barrier. That barrier is nothing but some sort of a membrane, and through this membrane the mass transfer is taking place. So again diffusion through the solid is taking place. So we have a listless examples, maybe leaching operation, maybe a crystallization operation, maybe adsorption operation, maybe electrophoresis operation, maybe chromatographic separation, maybe membrane separations operations, and maybe so we have several of the examples where the diffusion through the solids are taking place. So what we do in the next class, we will discuss about how the diffusion through the solids are taking place. So that's what we are going to discuss in the next class. So thank you very much for your patience hearing. Thank you. And what I am doing now, I am giving lot of problems as assignment. Maybe you can sit, and I have given around 35 problems. You can sit and you can solve it one by one, and as you practice it more and more, then you will get lot of interest on the course. Once if you get interest on the mass transfer course, then obviously you will be getting a lot of interest on the heat transfer as well as the momentum transfer. That way we are going to learn about whole chemical engineering, and we can do a lot of things in the chemical engineering. Thank you very much.